Have you ever stopped to think about what temperature really is? Or how the air inside a balloon, which feels like absolutely nothing, can push back with enough force to keep the whole thing inflated? Well, today, we're diving deep into the kinetic theory of gases. It's this amazing idea that connects the wild, chaotic, invisible world of zipping molecules to the pressures and temperatures we can actually see and feel every single day.
And that's the whole magic of it, right? Kinetic theory is this incredible bridge. It takes the microscopic actions of individual atoms, things we can't possibly see or track, and connects them to the macroscopic world of gases, the pressure, volume, and temperature that we measure all the time. So here's our game plan. First, we're going to build that bridge between the micro and macro worlds. Then, we'll see exactly how pressure is born from just countless tiny collisions. After that, we'll uncover the true meaning of temperature, which is a huge aha moment. We'll look at the wild range of speeds molecules have, and finally, check out how they interact and store energy. Let's get started. Okay, let's jump right in. What's the big goal of kinetic theory? It's all about explaining the large-scale stuff we can actually measure, like the pressure a gas pushes on its container, by understanding what all of its tiniest parts, the molecules themselves, are doing collectively. Now, trying to track trillions upon trillions of molecules is, well, impossible. So we simplify. We come up with a model called an ideal gas. Just imagine molecules as tiny little points, like super small billiard balls, zipping around totally at random. They collide perfectly, but otherwise they don't attract or repel each other at all. This simple model is fantastic because it gets us to the famous ideal gas law, PV equals nRT. This equation works incredibly well for real gases at low densities, and it's the big macroscopic law we're aiming to build from the ground up. All right, now for our first major derivation. This is where we get to see how that steady, constant pressure we feel from a gas is really just the grand total of an unimaginable number of tiny individual molecules smacking into the walls of a container. So let's really ask the big question for this section. What is pressure on a molecular level? To us, it feels like a smooth, constant force. But its origin is pure chaos. It's born from countless tiny impacts happening every single nanosecond. To figure out where pressure comes from, we're going to follow this super logical path right here. We start small, with just one molecule hitting a wall and calculating its change in momentum. Then we figure out how often it hits that wall to find the average force from just that one molecule. After that, we just add up the forces from all the molecules, and finally divide by the area to get the total pressure. It's a beautiful way of building from one single particle up to the whole system. So let's kick off with step one. Imagine a single molecule with mass m and velocity vx heading for a wall. In an ideal gas, we assume it's a perfectly elastic collision. Think of a perfect billiard ball bounce. It hits the wall and reverses direction flawlessly. Its momentum going in was m times vx. Coming out, it's m times negative vx. So the total change for the molecule is minus 2m vx. But, and here's the key, thanks to Newton's third law, the momentum it gives to the wall is the exact opposite, plus 2m vx. That tiny little push is the fundamental source of pressure. Okay, after we run through all 5 of those steps, we land on this absolutely incredible result. This equation connects pressure, P, something we can easily measure in our world, to the microscopic world. Just look at what's on the right side. You've got N, the number of molecules, M, their mass, and V, the volume. And that VRMS term, that's the root mean square speed, which is just a special kind of average speed for the molecules. We use it because pressure is all about kinetic energy, which depends on speed squared. This formula right here is our first major bridge between those two worlds. Now, we take that pressure equation and we combine it with the ideal gas law we saw earlier. And when we do that, we get to what is honestly the conceptual peak of kinetic theory. We uncover the true physical meaning of temperature. Seriously, think about it. When you stick a thermometer into a room and it gives you a reading, what is it actually measuring? What fundamental property of that gas is it picking up on? It's not just some random number. The answer is all about the motion of its molecules. And here it is. This is the heart and soul of kinetic theory. The average kinetic energy of a molecule just moving through space, we call that its translational kinetic energy, is directly proportional to the absolute temperature T. That's it. Temperature is a measure of molecular motion. The little k in there is the Boltzmann constant. You can just think of it as a conversion factor that turns temperature units like Kelvin into energy units like joules. This one little equation completely redefines what we mean by temperature. And the implications here are massive. First off, temperature isn't some abstract thing. It is a direct measure of the average jiggling energy of molecules. The hotness you feel is literally the energy from atoms smacking into your skin. Second, at the same temperature, a big, heavy oxygen molecule and a tiny, light helium atom have the exact same average kinetic energy. Think about that. That means the little helium atom has to be moving way faster on average to make up for its small mass. This is why light gases like helium can escape Earth's atmosphere, while heavy ones like oxygen are stuck here. And finally, it tells us what absolute zero really means. At 0 Kelvin, all that random translational motion would just stop.
So, we've been throwing around terms like average kinetic energy and root mean square speed. But let's be real, in any gas, there's a huge range of speeds. Some molecules are barely moving, some are cruising near the average, and a few are moving at absolutely insane speeds. This section is all about understanding that spread.
The genius who first figured this all out was James Clerk Maxwell. He came up with a mathematical function, P of V, that tells us the probability of finding a molecule moving at any particular speed, V. It's a statistical law that brings a beautiful order to all that molecular chaos. And when we graph it, we get a really clear picture of how speeds are spread out in a gas.
Now, when we look at this distribution graph, there are 3 key speeds we talk about. The most probable speed, Vp, is right at the peak of the curve. It's the speed that the most molecules have. The average speed, V average, is exactly what it sounds like, the simple mean. And the RMS speed, V RMS, the one from our pressure equation, is always a bit higher because it gives more weight to those faster-moving molecules.
So the crucial thing to get here is that these 3 speeds are not the same. For oxygen at room temp, for example, the most probable speed is about 395 meters per second. The average is 445, and the RMS speed is the fastest of all at 483. This just shows you how the distribution curve isn't symmetrical. It has this long tail of high-speed molecules that pulls the average and especially the RMS speed over to the right of the peak.
And that high-speed tail, it is unbelievably important. The text gives 2 perfect examples. In a puddle of water, it's only the fastest-moving molecules in that tail that have enough energy to break free and evaporate. That's what makes clouds and rain possible. And inside the sun, it's only the very fastest protons, way out in the tail of their distribution, that can slam into each other hard enough to fuse together. That's literally why the sun shines.
Okay, so up until now, we've kind of been treating molecules like tiny, simple dots. But now let's get a bit more realistic. Let's look at what happens when they actually collide and how more complicated molecules can store energy in ways other than just flying in a straight line.
So here's a great question. If molecules are moving at hundreds of meters per second, why does it take a minute for you to smell perfume from across a room? The answer is something called the mean free path, or lambda. A molecule doesn't just travel in a straight line. It's constantly smashing into other molecules, creating this crazy random zigzag path. Lambda is just the average distance it travels between those collisions. For air at sea level, it's a tiny fraction of a millimeter, which is why diffusion happens so slowly.
Now, when molecules collide, they don't just bounce. They share energy. But how do they hold on to that energy? This brings us to a cool idea called degrees of freedom. It's just a fancy way of saying the different ways a molecule can move and store energy. A simple atom can only move up, down, left, right, and forward, back. That's 3 translational degrees of freedom. And there's this key idea called the Equipartition of energy theorem, which basically says energy gets shared equally among all the available options. On average, each degree of freedom gets an energy of 1/2 K times T.
But more complicated molecules have more options. A diatomic molecule, like an oxygen molecule, can also tumble end over end in 2 different ways. That gives it 2 rotational degrees of freedom, for a total of 5. A more complex molecule can rotate in 3 ways, giving it 6 total. As you can see in this table, the more degrees of freedom a molecule has, the more ways it can store energy, and this directly affects a property we call its molar specific heat, or CV. Now, there are 2 main ways we measure this specific heat. First, there's CV, which is at constant volume. Imagine heating a gas in a sealed, rigid steel box. Since the gas can't expand, every bit of heat you add goes directly into making its molecules jiggle faster. It all becomes internal energy. But now consider CP, at constant pressure. This is like heating a gas in a balloon. As you add heat, the gas doesn't just get hotter, it also expands, doing work on the balloon. So the heat you add has to do 2 jobs, increase the internal energy and provide the energy for that expansion. That's why CP is always bigger than CV. Wow, okay, we have covered a ton of ground. So let's pull it all together and do a quick recap of the core ideas and relationships that we've built throughout this journey.
All right, one final super important process that ties these ideas together is an adiabatic process. This is what happens when a gas expands or gets compressed so fast that there's no time for heat to get in or out. The best example? The psst sound when you open a can of soda. The gas expands instantly, doing work on the air around it. But where does the energy for that work come from? It comes from the gas's own internal energy. The molecules literally slow down, the gas gets colder, and that's why you sometimes see that little puff of condensed water vapor. So let's do a rapid-fire review of our mathematical toolkit. We started with the ideal gas law, our big picture target. We then derived the link between pressure and molecular speed. We uncovered the fundamental meaning of temperature as kinetic energy, which then gave us an equation for the RMS speed. We explored how energy storage changes specific heats, and we finished with the relationship for those super-fast adiabatic processes. These equations right here are the backbone of kinetic theory.
So at the end of the day, kinetic theory is a total triumph of bottom-up thinking. It takes the simple, chaotic actions of countless individual particles and shows how they give rise to the stable, predictable laws of our macroscopic world. And that leaves us with one final thought to chew on. What other complex systems, maybe in economics or biology or even in our own societies, could we understand better if we could just figure out the simple rules that govern their smallest, most fundamental parts?